So I'm Houston Putman. I'm from Bloomberg, and I'm here today to talk about running Solr on Kubernetes. I guess I'll just start off with a little bit about Bloomberg, where I work. If you haven't heard of us before, we are the largest provider of financial news and information across the world. Our strength is providing to our clients highly accurate kind of financial news and data aggregation so that they can kind of do the business that they need to do. And in general, so that we can provide this information, we need to create high performance information retrieval systems to give them this data. So kind of as a part of that, I work for the Bloomberg search infrastructure team. We power hundreds of hundreds of applications throughout the rest of the company that use search and Zookeeper. The use cases that we kind of solve for are very diverse in both kind of the problems that they're trying to solve and the scale at which we need to solve that problem for. And as we've been kind of going through the company, replacing the search engines that other people have been using, we've been displacing other technologies, a lot of enterprise technologies, and trying to replace it with these open source solutions such as Solr and Zookeeper. But just to get down to the numbers of what we do, we run kind of tens of thousands of Solr instances across the company. These run on thousands of servers that we manage within our own data centers. And these contain tens of billions or hundreds of billions of documents. Daily, we have our clients ingesting hundreds of millions or billions of new documents into their clouds and into their collections, which kind of enable tens of thousands of queries per second across all of our different use cases. And in general, the services that we provide are critical to Bloomberg and the global financial markets. So when we're running these tens of thousands of Solr instances, we need to make sure that, one, they're managed very well and very robustly so that they're reliable and they don't go down and crash the global financial markets. That'd be really bad. So that's kind of what we're talking about here today. Running Solr in a way that is kind of not awful for us as search infrastructure providers running thousands of Solr instances. We want to be able to kind of automate the process of managing these Solr clusters so that we can get to kind of the actual fun part of modifying Solr, making search like features better for our clients, and not necessarily go into boxes maintaining these different search applications. And so the ultimate goal of what we're trying to get to here at this talk is automating Solr Cloud and using Kubernetes to do this. First, I'll just kind of start off by talking about how Solr Clouds are managed and the different kind of tools available to within Solr to kind of do this management, both implicitly and explicitly. Then we'll bring Kubernetes into play and kind of explain how it fills the gaps of the current functionality that Solr provides for management. We'll then kind of show how the different constructs in Kubernetes can be built up so that we can actually deploy a Solr cloud within Kubernetes, and then obviously how we can automate it. At the end, we'll point out some of the new features that we have available that are kind of starting to generate a wider Solr ecosystem within Kubernetes, kind of trying to make Kubernetes the one-stop shop to how you run Solr in a robust and reliable way. So without further ado, managing Solr Clouds. I'm sure that a lot of you manage Solr Clouds yourself, but basically there's two different ways of looking at it. In general, what we really care about here is the data that we're trying to provide to our customers. But there's two different ways to look at this data. You can look at both through a physical topology as well as a logical topology. The physical topology is kind of like the old style way of running Solr with like master-slave. You have Solr nodes that are running and cores that are running on those Solr nodes. Basically, the Solr nodes are a Java process running Solr that are connected to Zookeeper. And the cores are just data directories that live within that Solr node that host and indexes data that is then indexed to by the client and queried from, obviously. The logic topology is what we generally think of when we think of Solr Cloud. We have a series of collections. Collections are nothing more than data that shares a common schema Shards are ways to break down collections into smaller bits so that they can be stored in a better way, and kind of we have more parallelism in our requests. Replicas are basically just copies of a shard's data. So two replicas of the same shard will have exactly the same data eventually, and then two replicas of different shards will have completely different data. But in the end, replicas and cores are basically the same thing. And so if we look at the logical topology, which, as you can see here, we have two collections. One is 4-sharded, one is 1-sharded, and they each have a various number of replicas. If we take away basically all the extraneous information and just look at the data, which is the replicas and cores are basically the same thing. We switch it around. We can apply on top of it the physical topology. And just from this view, we can see that we're managing the same thing in two different ways here. And so if we look at the actual ways that Solr gives us to manage these topologies, we can see it's not evenly distributed. The logical topology has a lot of features within Solr for management. The implicit root gives us auto-scaling. This means that we can automatically spin up new replicas when we have high query traffic. We can basically split shards if they get too big, so on. And then time-routed alias gives us the ability to create new collections based off of the data that's coming into our collections. But there's also a lot of explicit commands that gives us kind of access to the logical topology, which is a lot of it through the collections API. So we can manually create new collections, manually split shards, manually add new replicas, move replicas around, and so on. But on the physical side, there's not a whole lot we can do. We can use auto-scaling to shuffle replicas across nodes. We can use the collections API to manually migrate all the replicas from one node to another. But in general, there's a lot of stuff missing here. We want to be able to automatically spin up new Solr nodes. We want to be able to kind of automatically move to new machines when we are kind of at capacity on machine. But these are things that Solr can't really do itself. This is because Solr is running inside the JVM and it really doesn't know how you've deployed it. So this is not something you can really do within Solr. And so this is why you need to look at external technologies. And surprise, surprise, we looked at Kubernetes. So I'm sure a lot of y'all have heard of Kubernetes. You've been to other talks here talking about Kubernetes, such as Emirates. But basically, I'll briefly describe it. Kubernetes is an open source platform that allows managing of all your different resources. This is managing of networks, managing of processes in a way so that you can declaratively tell your system what should be run, and you don't necessarily have to go onto machines and make sure that it happens. Kubernetes has abstracted all this away so that you can plug and play with different kind of interfaces to declaratively build out your cluster in a very version controlled and safe way. We'll talk about later, but there are automatic processes that you can run in Kubernetes to do things that are not necessarily as declarative, but we'll get to that at the end. Okay, so Kubernetes at the core of it is running applications. And in Kubernetes, if you've been to other talks here, the base of running a application with a Kubernetes is running a container. This could be a Docker container, Rock container, any of these different types of containers. But in general, a container just runs one or more processes in a very isolated and kind of permissioned way. So you can isolate a lot of the external variables, such as what else is running on these machines. And you can just kind of constrain a container to do a particular task or set of tasks. However, there's a lot of functionality that a container doesn't set up for you in a kind of overall system, such as volume management and network management. So Kubernetes has created a pod on top of this. So we'll just start using Solr as our example because that's why y'all are all here. So for example, if we want to start running Solr in Kubernetes, we obviously need to make a Solr container. We need to run the Solr container within Kubernetes, but we have to have these containers be able to talk to each other. We need to be able to kind of store data with these Solr containers because otherwise you have no index data to actually serve requests. That wouldn't make any sense. So Kubernetes has an abstract called a pod, which allows you consistent network and storage interfaces to containers within these pods. It can also keep track of your container's health. So you can have Solr 8 Plus has a liveness, a health check handler now. And so you can configure your pod, your Solr pod, to every 10 seconds call this liveness check handler in Solr to make sure that Solr is working. And if it's not, kill the pod. But that's not really what we want, right? We want our Solr to be reliable. We want it to be running all the time because our clients are always hitting it. And so if Kubernetes is going to automatically kill this pod when something goes wrong, we want it to come back up, right? Well, obviously, Kubernetes comes with ways to do that. And the easiest way is just using a replica set. A replica set does mostly just running in instances of a pod. And so I say I want to run 3 instances, 3 Solr nodes in a cloud. I could put in a replica set, give it 3 instances, and the Solr pod specification, and it will 3 Solr pods will be created. However, if one of them dies, say long GC, out of memory crash, whatever, the pod will go away because Kubernetes kills pods that go bad. And the replica set will then create a new pod, pod 4, which basically maintains the consistency that we want 3 Solr pods running at any given time. And this is nice. So now we can run in instances of Solr at any given time. However, this isn't the only way to make a system resilient and reliant. We need to be able to do kind of basic things like rolling upgrades. So if I want to push out a new version of Solr, I'm going to upgrade from Solr 7.5 to 7.6. I don't want to go and just create a whole new replica set and delete the previous one, because at that point, I could have a bad version of Solr I'm pushing in. And if I'm upgrading all my pods at the same time, then things are going to go bad. And so Kubernetes has thought about this, and there's another abstraction on top of replica sets that's created called a deployment. And so a deployment manages replica sets. So you're given a pod specification and replica count much like a replica set, and the deployment will create a replica set with those inputs. However, if you kind of give the pod specification an update, such as upgrading the container version that you're using for Solr, it will create a new replica set. So the pod specification is versioned now, and it will try to, one by one, remove pods from the first replica set and add them to the second replica set. If, say, for example, the pod 5, which is the new version of Solr that we're trying to run, has some type of error and it doesn't actually start up, we will still have 2 instances of the Solr 7.5 pod running to make sure that our clients are still able to hit Solr. And so at this point, let's assume everything's going correct, and one by one, we end up with 3 Solr nodes in our second replica set. The first replica set is kept around just to make sure you can do safe downgrades if something else bad happens with the new version of Solr that you're pushing. But in general, we have safe upgrades, we have resilient ways of running Solr, and things are looking pretty good. However, as I mentioned before, or maybe I forgot, I'm sorry, pods aren't actually addressable. We need kind of to manage the internal networking. So Kubernetes does a lot of things for you. It solves a lot of problems, but it isn't just like the end-all be-all one Band-Aid to slap on. There's a lot of caveats that come with that. And with one of the big ones is managing networking within Kubernetes. It's not straightforward. There's a lot of things, hoops that you have to go through, but in general, the base rules that you have to understand is pods are not necessarily themselves addressable. This is mainly for security reasons, but you have to create an abstraction on top of a pod called a service, which adds basically DNS rules and IP addresses for a set of pods that you want to route requests to. And so, as you can see here, we have a Solr deployment with 4 pods, 1 leader and 3 followers. And we have 1 service that routes requests just to the leader pod and 1 follower service that routes requests to the 3 follower pods. And so with these two services, a DNS entry is created inside Kubernetes so that other applications within Kubernetes have access to send HTTP or TCP requests through those services and down to the pods below them. Cool. But we don't just run things within Kubernetes. At some point, you need to be able to have an external HTTP traffic hit internal processes within your cluster. Be this like from the UI that's running in your client's browser, be it from other applications that are running in other Kubernetes clusters, for example. And one way of adding external addressability is through ingresses. And this is needed because services that we mentioned in the previous slide don't actually give external addressability. They only give internal addressability within a Kubernetes cluster. And so within ingress, you can add basically HTTP rules. It doesn't work with raw TCP. It only works with HTTP. You give ingress rules such as an HTTP hostname or a path in your HTTP request. And those rules map to individual services within your Kubernetes cluster. So for example, we have a rule that says any HTTP traffic that comes into our Kubernetes cluster with the host name host1 gets routed to service A, which might be, for example, one Solr cloud, and anything with the ingress host2, the host name host2 gets routed to service B, which might be a different Solr cloud. So now we have the ability to talk from outside of Kubernetes into Kubernetes to talk to our Solr pods. So is this basically everything that we need to build Solr? Unfortunately not. These kind of base building blocks that Kubernetes has given us, and it's not all of the base building blocks, but kind of a lot of the important ones, are really good for building stateless applications. One good example of a stateless application is the Solr Prometheus exporter. Basically, all you give it is a configuration and a zookeeper to hit, and it will go and fetch metrics from each of your Solr nodes. But stateful services, a lot like Solr, Zookeeper, Kafka, any of these type of things, come with a lot more information, and you need some additional features within these Kubernetes resources to be able to run them. One big thing is persisted and local data. Solr obviously has indexed data, and you want to be able to keep and persist this data even if your node restarts. Maybe not if you're using the stuff that Yannick was talking about this morning, but for the stuff we're doing here, you definitely want to keep your data around. But also, I'm sure running Solr Cloud, you know, Solr Cloud nodes are kind of identified by the URLs they can be hit by. And so if you have a pod or Solr node restart, you need to have that Solr node keep the same address when it comes back up, or else you'll have a lot of orphaned replicas that aren't living anywhere, and you'll have a lot of new replicas that are living on a brand new host that no one knows about. Things get bad. Solr was not built to do that. And so basically, we need pods that have kind of consistent identity and addressability, even if they're restarted. So what can we do about these? With persisting data, Kubernetes has thought about it a lot, and they have options. So basically, the workflow in Kubernetes is twofold. There is a persistent volume and a persistent volume claim. Persistent volumes allow you to store data persisted irrespective of the applications that are using it. So say, for example, you have a pod that is connected to a persistent volume. The pod restarts 5 times. The data within that volume does not go away like a lot of other volumes in Kubernetes, which are ephemeral. The persistent volume claim is a powerful tool to using these persistent volumes. So instead of having to manually add persistent volumes connected to your pods yourselves, Kubernetes lets you attach a persistent volume claim to, say, a deployment or a pod or any of these things, and say, I want to have a persistent volume with these set of rules. So for example, I want a persistent volume with 50 gigabytes or more space available, and let Kubernetes find an available persistent volume and map it to your pod and bind it for you so that no one else can use that persistent volume. These are kind of, this workflow is very powerful and lets you do a lot of cool stuff. And the different cloud providers that have like Kubernetes running, such as Google Cloud, Amazon, AWS, Azure have created their own kind of types of persistent volumes that work well on their systems. There's also kind of standard ones like NFS, OpenEBS, a lot of other types. There's a lot of options for persistent volumes out there, which makes sense because everyone stores data differently. So running stateful applications isn't just about the data. We talked about kind of consistent addressability and identity. So stateful sets are kind of a reimagining of replica sets and deployments, which let you kind of use Kubernetes in a more stateful way, unsurprisingly. So you're able to attach a persistent volume claim to your stateful set, and at this point, Kubernetes will create your kind of replicas in pods that you want from this replicas. The stateful set, and then map an individual persistent volume to each of those pods that meets that persistent volume claim that you specified. So if you're using just a deployment and you give it a persistent volume claim, that will map one persistent volume to all of the pods that come from your deployment. Stateful sets let you have individual data for each of the pods that you're running, which is very nice when you're running applications like Solr, where the data is different on each of the pods that's running within the Solr cloud. And also pods are iteratively named, so the first one will be pod 0, pod 1, etc. And so if a pod actually dies within a stateful set, the persistent volume claim for that pod doesn't die. It stays around, as we mentioned before, still connected to that persistent volume. And so when the pod comes back up with the same name, which is very important, as we mentioned, it's still connected to that same data source. And so when it connects back to Zookeeper, it will still say, I have the same replicas available on this node, and everything will continue as if the pod never restarted at all. Cool. So we're getting pretty close here. But as I mentioned before, two things. Networking within Kubernetes is not straightforward. It's not easy. Two, Solr nodes need to be individually addressable, and the addressing of them needs to be consistent. And so there's something that Kubernetes provides along with stateful sets, which is called a headless service. And this is a service that you can connect with a stateful set that basically gives a unique DNS entry for each of the pods in the stateful set, which is awesome. That's exactly what we need for Solr. The only problem is it doesn't work with ingresses or service load balancers. And so, say for example, we want to run Solr across two Kubernetes clusters. When a Solr node is doing peer sync from another Solr node, you need to be able to have an external connection so that the nodes can talk to each other across Kubernetes clusters. And there's two options for this, load balancers and ingresses. And I already explained ingresses earlier, which allow for custom hostname or path routing for an HTTP headers into the Kubernetes cluster and map them to services. Services also can be set up with a load balancer, which creates external IP addresses. Amran talked about this in his talk as well, but basically the thing we don't like about this is you have to create individual IP addresses for each of your Solr nodes, and if you're running thousands of Solr nodes, that's thousands of unique IP addresses, and if you're running this in a public cloud, that could be expensive, and we don't like wasting money here. So we like ingresses. And so basically with I forgot to mention, since we can't use headless services, we're going to have to, unfortunately, create an individual service for every Solr node or pod within your Solr cloud. And so when we actually build up a Solr cloud within Kubernetes, we end up with this. We have a stateful set at the bottom, which is managing in Solr nodes or pods. So let's say we have a Solr cloud with size 3. So we have 3 Solr nodes here, which are run in pods. They are also mapped to persistent volumes, but we didn't have enough space to put that here. And each of these has a service that allows it to be addressed both internally and externally. And we have one common service, so if you just want to hit any of your Solr cloud nodes and you don't care which one it is, you can just go through that common service. And these are exposed externally through ingress rules. And here we have nice common sense HTTP host names. test/Solr, test node 0/Solr, and so on. And so now we can individually address each node. And so client requests come from outside the cluster, hit one of these ingress rules, and go down into the correct pod that they need to hit. However, this also works if we need to do peer sync, as I was saying before. Say pod 1 needs to talk to pod 2 to get information from a leader replica. And so pod 2 is addressed by the ingress rule that was made for it. So the actual Solr node within Kubernetes, within Solr Cloud is named that ingress rule. And so pod 1 will know to go outside back to the ingress, which routes through that ingress rule down to pod 2. And so at this point, we're able to do internal and external communication for Solr clouds and run them, run one Solr cloud across multiple Kubernetes clusters, which is awesome. The only problem here is, as you can see, it would be nice if we could kind of eliminate the middleman and not have to go through these ingresses and all these additional routes to just do peer sync between two pods that are running in the same Kubernetes cluster. But we can get to that optimization later. So what exactly have we built here? We have a stateful set that is running in nodes in pods of Solr Cloud nodes. We have a service for each of these pods, as well as a common service and a somewhat worthless headless service at this point. And then we have an ingress that has rules for each of our services that make them externally available. I'm going to bring this back up at some point, so I'll move on. But this is a lot of stuff to manage, and the whole point of doing this in Kubernetes was so that we didn't have to manage it ourselves. So I guess the question is, can we automate this? And what we kind of want in the end is just to be able to say, give a specification for your Solr. Say we want 4 replicas running Solr 8.1.1 connecting to this zookeeper that we managed independently. And that would be awesome if we did that, push it in, and get this Solr Cloud back. And there are things that can do this, like I know LucidWorks uses Helm to do this. We, as you will see in the future, use something else. But we don't necessarily just want to be able to create Solr Clouds in an automated way. That's a lot of things to keep track of if we're trying to monitor the health of it, do all these other things. And so we want to be able to kind of automate the tracking of the status of the Solr Cloud as well. So we want to basically put in the specification and get back a status that tells us, how do I connect to this Solr Cloud? How many of the replicas are running? Which replicas are working, which are failing? What is the version of each replica? Kind of like default information that you don't want to have to go and scrape yourself. And kind of we want that to be automated. So in the end, the answer is we can automate it all. Basically, Kubernetes gives us a lot of power to do this. And these are through things called custom resource definitions. So everything I've mentioned in this slide deck previously, dealing with Kubernetes, such as ingresses, services, deployments, replica sets, all these things are Kubernetes resources. And so custom resource definitions, or CRDs as they're commonly called, are basically ways of making your own resources within Kubernetes, because Kubernetes has no idea what a Solr is, what a Zookeeper is, what a Kafka is. But we do. And so we can create our own resources and then create controllers, which are basically management for these resources, because even if we create a Solr in Kubernetes, Kubernetes doesn't know how to make a Solr happen. And so controllers are the things that kind of listen to Kubernetes, and Kubernetes will tell it whenever a new Solr CRD is inserted, a new one is, one of them that is already there is modified, one of them is deleted, and then the controller will go and use the other resources within Kubernetes, such as pods, stateful sets, deployment services, and it will use these things to create a Solr Cloud for us, which is, this thing that we've created already. So basically, the controller is the thing that maps the specification for a Solr Cloud to the actual resource that need to be created in order to run it. And then it also generates that nice status that we looked at the previous slide. An operator is nothing more than a grouping of controllers that work for a similar purpose and technology. So the Solr operator, for example, has a controller for Solr clouds, Solr backups, in the future Solr restores, collections, and metrics. And so yeah, in general, we have created the Solr Cloud operator. It's open sourced. We have some community involvement, but we have 2 resources available right now. We can run Solr clouds with persistent volumes, and it works across multiple Kubernetes clusters. And we also have recently added backup support. I'll get into the backup a little bit later. It's a little complicated. There's currently PRs in for adding Prometheus metrics exporter resources so that you can kind of monitor the metrics within your own Kubernetes cluster, like Emmerich was talking about earlier, as well as monitor Solr clouds outside of the Kubernetes cluster, because you're not going to migrate everything into Kubernetes at once. We want to make this kind of pluggable so you can use the parts of the Solr operator that you want within Kubernetes and still kind of manage your own, manage the old style way, the stuff that you want to, while you're migrating everything over. Because we're not going to go at Bloomberg and migrate all of our Solr clouds in Kubernetes day one. We're going to start monitoring them in Kubernetes and slowly move out the way that we manage these things. So, and then we also have, thanks to Zane Williamson, a PR in to have a Solr collection CRD, which can hopefully kind of become an awesome way of kind of joining the way that Solr Cloud does its distributed management and kind of like spinning up new replicas and shards and that kind of stuff, and add that, kind of merge the logic between the Solr operator and Solr Cloud in that way. And in general, we love contributions. So this is I'll talk about it a little bit later, but this is a product that we really want to be owned and driven by the community so that it can help solve a lot of people's issues running Solr. Because at Bloomberg, we run Solr for a lot of different use cases. We run it in a smaller number of ways. And so we obviously don't have the reach and kind of the use cases to solve everyone's problems. So we need other people in the community to come and help us build this out to be an extremely generic and multifaceted way of running Solr Cloud. But yeah, so getting back into this additional things that we've added, and these are new since the last time I've presented this had buzzwords, there's the 2 new resources that we talked about. There's the Solr metrics exporter as well as the Solr backup. So let's do metrics first because it's a lot easier. As I said before in this talk, the Prometheus exporter for Solr is a stateless service, and in Kubernetes, that's very easy to run. And so given a Prometheus exporter resource that we've created, we can easily just spin up a deployment of this Prometheus exporter, put a service in front of it, and if you all attended Emmerich talk, you can easily set up Prometheus to scrape things within Kubernetes and scrape services. And so if you add certain roles to your Prometheus Kubernetes configuration and start submitting Prometheus exporter resources to the Solr operator, you'll automatically be able to scrape metrics for the Solr clouds running inside and outside of your cluster, which is, in my opinion, awesome. Backups are a little more complicated, as you would imagine. So if you've done Solr Cloud backups before, you know there's collections APIs calls that you can use to do backups. These require either running Solr on an NFS file system or on HDFS. I don't know anyone that actually does the HDFS stuff, so we went with NFS. So basically, you don't actually need to run Solr on NFS. You need to have Solr have access to a directory of shared data across all the other nodes in your Solr cluster. And so there's a couple different ways that Kubernetes lets you do this through different types of volumes, such as read-write many persistent volumes, NFS volumes, etc. And if you mount that, give that volume to your Solr cloud, we can mount it and then perform backups via the collections API. And then via Kubernetes job, we will then kind of tar up and zip that data and then either ship it to another volume or upload it to an S3 compatible endpoint. There's a lot more data information than just this one slide. It's a pretty easy workflow using it with the Solr operator. But if I'm running out of time, so if you want to talk about that, please catch me later. But yeah, for the future of the project, we want to make optimizations, obviously, integrate better with Kubernetes. Kubernetes is kind of evolving very quickly. We need to keep it up to date, as well as with the operator infrastructure that exists for Kubernetes. And a future goal is to make Solr more cloud native, make it work better with Kubernetes in a various number of ways. But to do that, we need a lot of collaboration. So please come talk to us if you're interested. We have a lot of ideas and not a whole lot of time. So more people, good. Awesome. Any questions? I think we have a couple of minutes. Sure.
You mentioned that regarding the stateful set, is it have the same functionality as the deployment? You mentioned like upgrade. You have deployment?
Yeah. So I guess the question is, does stateful sets have the same functionality as deployment? I would say yes, with more features. Stateful sets were made after deployments, and so basically the same. You can do everything you can with the deployment plus more of the stateful set. It just comes with a little more baggage as well. So I think the Solr operator doesn't necessarily. So there's the kind of PR in to use to add a Solr collection CRD, and that I think does work with auto scaling. But in general, as I said, there were two topologies: the logical, physical. The Solr operator right now is just working mainly with the physical and doesn't really deal too much with the auto scaling topological. Logical topology stuff. But we can definitely make it integrate better. Yeah, so the question was around how does the auto-scaling work with the other stuff in the operator, like do we get bigger volumes if we need them? I would say the auto-scaling is not good yet. I mean, there's no horizontal auto-scaling or vertical auto-scaling or anything like that. And I think there would be a need for a much kind of closer integration with Solr to make that happen. I would not say it's easy right now. So yeah, I think you would need hooks to kind of determine the size of the volumes that you need, and then give that back to the controller to update the size of the volume that you're asking for.
You have unlimited stores, unlimited volumes.
Yeah.
Are there other limitations that makes it hard?
I don't think so, no. I think it's mainly due to volume management in Kubernetes. We can take this one offline, though.
I think you mentioned that you have 100 Solr clusters. Is that correct?
We have more than that, yeah.
Is there a reason you don't just have one? Are you working on scaling?
So one Solr cluster across thousands of machines, I would be very scared to run. It's much easier to maintain smaller Solr clusters in my kind of view of it. And we have a lot of various tenants that are using these. And so you don't want to group, let's say, well, we don't want to group 1,000 of our clients on one Solr cloud so that, say, for example, one of them causes OOMs in a various number of the nodes and causes other people's to crash. It's much safer for us to have these running in separate JVMs. And
It's more for security than it is.
security, reliability, kind of ease of life. I don't know. Well, yeah, thank you for joining us. Enjoy the rest of your Activate.